Okay, let's look at a couple of these web work problems that were due today. Gandalf. Look at Gandalf. All right, so in these problems, pictures are going to be a really important aspect to visualize what's going on, and then when you have a good picture, then you'll be able to recognize what tool or tools will apply. Okay, so we got. He's going to start at 1, in my example here, he starts at 1, 0. And he wants to end up at 3, 4. Something like this. So he's starting here at P. He wants to end at Q. And he's going to go in the direction, he's going to start in the direction 3, 1. So what does that mean? For every 3 units to the east, he's going to go 1 unit north, right? So 3, 1, for every change of x of 3, his change in y is going to be 1, right? That's what vector components mean. They mean amount of change in each direction, right? Amount of change. Okay, so he's going to head off in this direction. Something like this. And this is the vector 3, 1. Okay, and so then he changes direction only once and turns at a right angle. So he's heading this way. He's going to make 1 turn at a right angle and then head straight for Q. So maybe that's right about here. Would you agree? So we'll call this point R. Right angle turn. R for right angle. What are the coordinates of that point? R. So he's going to be walking this way, and then he's going to turn, and then he's going to walk this way. So you can set up. So there's a few ways to do this. One involves setting up a bunch of equations and variables and solving a multi-system equation. That's not your easiest way to do this. Okay, what you need to recognize here is, so what do we really need? We really need this vector right here. If we got this vector right here, point R is a breeze, right? Because we have the tail of the vector, and now we have the vector, so we can find its tip, which would be point R. So the question is, how can we get that vector? That's parallel to V, and we know this is a right angle. Yeah, so what you need to see is that red vector that I just drew is the scalar projection of what vector? PQ. So that's the scalar projection, vector projection of PQ, the blue vector, onto what? V, right? V. So vector V, really just, for our purposes, is just this direction, right? It's just this line. Just this direction. So we want to project that blue vector onto V, 3, 1. And when we do that, we'll get the red vector. So if this V were 9, 3, if it were -6, -2, if it were 30, 10, the vector projection of the blue one onto the vector projection onto any vector parallel to V is still going to be that red one. Do you see that? Say it again. The vector projection of PQ onto any vector parallel to V is going to give you the same red vector. Whether this is 100 units long or it goes this way, negative, a hundredth of a unit, or negative 50 units this way, 3 units that way, it doesn't matter. When you project, when you project onto a vector, you're essentially just projecting onto the line parallel to the vector, and you get the same vector every time. So we can just project it onto this vector, and we'll get the red vector. So we're going to project PQ onto V. And that will give us the red vector. And then we have point P. The red vector gives us the coordinates of point R easily. Questions on that one? So that's the roadmap for that problem. So what's hard about this? Recognizing how vector projection is the key to solving it, right? So it's getting used to what is vector projection? Well, it's the component of one vector onto the direction of another, right? And then this would be then the component of PQ perpendicular to V, right? So this is the projection or the component of PQ parallel to V. And then this is the component of PQ that's perpendicular or orthogonal to V. Questions on Gandalf the Grey? Does it make sense? Okay, the next one. Find two unit vectors orthogonal to A and B. So you've got two vectors. So how about just one vector that's orthogonal to those? And then we can talk about two unit vectors later. So how about just if you got two vectors, we need to find a vector that's orthogonal to both of those. So yeah, yes, sir. That's exactly what the cross product gives us from last Thursday, remember? If you take the cross product of two vectors, you always get a vector orthogonal to both your original vectors. Or in other words, it's orthogonal to the plane formed by the two original vectors. Okay, and let's practice that. So remember, so it's any way that you can find the determinant of this matrix. So we're going to do the standard the unit basis vector, ijk, and then the first vector, -1, -1, 5. Then the second vector, 0, 3, 1. Any way that you can find the determinant of that vector will give you the components of the cross product. I like to do this. I like to write the first two columns again. And then I'm going to go, I've got three diagonals down to the right that have three terms or three factors. Then I have three products down to the left that have three factors. So my I, so I can group my i's together here. So I is -I here. And then on the backwards one, I got 15i, but that's going to be minus. So minus 15i. Forward j is going to be 0. Forward, backward, this way. It's going to be j times -1 times 1. That'll be plus j. Forward k would be -3 this way. And 0 that way. So minus 3k. So what do I got? I've got -16 in my example. 1, -3. Did I do the math right? So what is this? This is a vector, what? Orthogonal to both A and B. And by the right-hand rule, if I pointed my fingers in the direction of A so that I could curl them towards B, my thumb would be pointing in exactly this direction. Okay? All right, so now they want two, instead of just a vector that's orthogonal to both, two unit vectors. So I've got an orthogonal vector to both, but what I need is two unit vectors. So what I want to do is I want to scale this into a unit vector. I want to scale this into a unit vector. So if that were 100 units long, then what would I need to do that to make it a unit vector? I'd take 1/100th of it, right? 1/100th. If it were 5 units long, I need to take 1/5 of that. So whatever number of units this is long, I'm going to take that many of it. 16 squared plus 1 squared plus 3 squared. So that's my scaling multiple to get this from whatever length it is to length 1, right? So there's one of them, right? There's a unit vector that's orthogonal to both the original. And I think they said, enter your answer so that the first non-zero coordinate is positive, or the first vector is positive. So is this going to be my first vector or my second vector? That's going to be my second, because it's going to have a negative first component. And then how do I get the other unit vector with a positive first component? Just take the opposite of all the components. Just take the opposite of all the components. I have another unit vector in exactly the opposite direction, which then would also be orthogonal to the original too. And remember, with web work, you can put in expressions. Like, so if you punch this all in by hand and then use a decimal approximation, you're welcoming the possibility of errors along the way. So for instance, I could just put in -16 divided by square root of 256 plus 1 plus 9. Yeah. You can let web work be your calculator. Let web work be your calculator. And remember, use the preview answer. So now I've got this very difficult to read horizontal expression. Use the preview. Make sure it's what you wanted. And that gives you a nice image of it. Yes, that's what I wanted. And make sure the other ones are right. Go from there. Yeah, so you could make a punching error, or you could round too much. If you put -0.98 in, maybe you needed that extra 1. Maybe you needed that 1 in the 1,000th place. Because you don't have to worry about that. If you just put the expression in, it gives you an exact result. And then you don't have to worry about making a mistake when you punch in your handheld. Okay, so web work, you can put in expressions and let web work be the calculator for you. All right, any more questions about the web work? Okay. So just as a roadmap here, so we're going to finish up cross product today and talk about lines in space, and then, is it about this? Go ahead, Dan. Yeah, I purposely didn't talk about that one for a reason. So let's hold off on the question, okay? Yeah. Okay. So in terms of a roadmap from here, so today we're going to finish up cross product and do lines in space. Thursday we'll continue with lines and planes in space. Next Tuesday we'll talk about other surfaces, and then next Thursday is our first exam. And so what we're going to do with the exam is we'll have a shortened lecture, maybe like 45 or 50 minutes, a week from Thursday, and then we'll all exodus down to the basement, and then you can work on the exam from 10 to 11:30. Okay. A couple of you might have a conflict. Just let me know. We'll give you a different time. So then next week for recitation. Tuesday would be like an optional recitation that anybody can go to, and it'll just be review stuff for the exam. Okay, so that way people on Tuesday don't have to go to one that Thursday don't have to go to. So you're all welcome to go to it or skip it, but it's going to be just some review problems, study session for the exam, optional, and then Thursday, we'll have the exam from about 10 to 11:30 downstairs. Does it make sense? And then this weekend, I'll post a bunch of practice problems from the review sections in the back of the book. But just know that the exam is not going to be some of those problems with different numbers. The exam is going to test your understanding of stuff, as well as your ability to solve problems, okay? So don't expect the exam to be like web work problems or book review problems with different numbers. Okay, I'm going to give you new situations maybe that you've never seen before, And you've got to take the principles that you've learned and solve the problem. Okay. So just be ready and think about that when you're studying. That when you're doing practice problems, don't be in the mindset of what do I do to get an answer when I get this type of problem. So you have to have the mindset of what do I need to understand about this? Why did he pick this problem as a good problem that tests my understanding of a principle or principles? Okay. So you got to get in the mindset of understanding rather than memorizing a procedure. Does this make sense? Okay. So let's talk about let's review the cross product versus the dot product. Start with the dot product. Dot product. What was our conclusion about what the dot product is or does? What is it? Yes, sir.
Magnitude of two vectors put together, but so much as they're in the same direction.
What is magnitude of two vectors?
It's when you multiply the two vectors together, it's that magnitude.
Right.
As much as they're in the same.
Okay, right. So it's the product of the magnitudes of the original vectors, but to the degree that they're in the same direction only, right? To the degree that they're in the same direction. So dot product is for quantities and applications, or so we'll just say quantities. That are optimized, maximized, something like that, when the contributing vectors are what? Right, in the same direction or parallel. And what about when the contributing vectors, and when are you going to get 0 for the dot product? When orthogonal. And we saw the main kind of application of this was what type of quantity? Yeah. Work, right? So if I want this desk right here, if I want to displace this vector, if I want to displace this desk from here to the door, what direction should I push on it? If I want to get the most bang for my buck, right? If I want to make this the most efficient, I'm going to push in the same direction as the door, right? So I want my force to have the same direction as the displacement of the desk, and then I get all my energy then goes towards the work of moving it to the door, okay? But if I push straight down on the desk and I push really hard, and I get to stand up on it and jump up and down on it, how about the work to move the desk to the door? No work. I'm exerting all this energy for no work on the desk. Why? Because the displacement vector is that way. My force is down, orthogonal to it. Okay? So what about cross product? Is for quantities that are optimized / maximized when the contributing vectors are so when am I going to get the biggest cross product? Yeah. When they're orthogonal, right? So there's certain situations in life where the original or the contributing vectors, we get the best or the maximum situation when those contributing vectors are orthogonal. And 0 when? Parallel, right? Either the same direction or opposite direction. And then remember, dot product, these are both the product of two vectors. Dot product gives you just a magnitude, just an amount. Cross product gives you a vector, okay? So the magnitude of that vector is what we're talking about here, right? That maximized quantity is the magnitude of the cross product. And there's actually two vectors that are orthogonal to both, and so the right-hand rule tells us which way that cross product vector points. Okay, so let's look at this. So application, torque. So torque is like amount of twisting force, So the classic example is turning a bolt, right? Turning a bolt. So this is called the lever arm, this pink one. Your lever arm vector is the vector r, they usually r. And our force vector so dot product or cross product. So what's going to maximize or optimize my twisting of this bolt? If those two vectors are in the same direction, parallel, or if they're orthogonal. You should see clearly that it's going to be the orthogonal situation. We want the force, that our most efficient use of our energy is to put the force this way, right? Put the force this way. So dot product, or I'm sorry, cross product. So the torque, the torque, that's a tau, Greek tau, is usually used for torque. It's a vector, is r cross f. So torque is a vector, and so if I applied which way does this cross product point? Out towards you or into the board, according to the right-hand rule? Out towards you or into the board? So again, I'm going to point I can point my fingers in the direction of r. I can do it this way, or I can do it this way. Which way? Exhibit 1 or Exhibit 2 will allow me to curl my fingers in the direction of the force. 2. So this one, if I do this, I curl down. If I do it this way, I curl up. And so I want this. And so which way is the resultant vector? Out of the board. Well, that's pretty cool, because when you twist a wrench counterclockwise, which way does the bolt go? Out. It loosens it. It comes out at you. See that? So the right-hand rule is exactly the way that threads on screws are oriented. That if you apply torque in a counterclockwise direction, the bolt comes out at you, and that's the direction of the cross product. See that? And what happens if I wanted to tighten this thing? If I wanted to tighten it, I'm going to have some force somehow pulling down this way. So it'd be this, and where does the bolt go? In, right? The bolt's going to screw in, and that's the direction of the cross product. So this torque thing that's the way that bolts are actually threaded. Okay, so now let's talk about the math here. So if I want just the magnitude of the torque, two ways, right? I could get the components. I could if I had these components, I could find the components of the cross product and then take the magnitude of that vector, right? So I could do my determinant, get a vector, and then just take the components and get the magnitude. Or what's another way to get the magnitude of the cross product? So it's going to be just like, so what is this? It's the product of the magnitudes in as much as they are in the orthogonal to each other, and as much as they are orthogonal to each other. Okay, so that would be sine. And remember, theta is the angle when the vectors are tail to tail. Angle between the vectors when they're tail to tail. Okay, so just imagine taking that force vector the way I have it and putting it tail to tail with that. And so where is our, if you imagine that, right? You can imagine taking this force vector and just moving it to here. Blue. Why am I do that? Right? So so you can see where the angle theta would be. That would be the angle theta there. So then which of these is the angle theta? Exhibit A or exhibit B? Exhibit B is the angle theta. And so does the fact that we're doing sine theta agree with our, right? So F sine theta would be this component here. So this distance right here is F sine theta, and that's the direction that's going to give us the actual torque. The part of F that's just pulling on the wrench, pulling straight down the axis of the wrench, gives us actually there's no contribution to turning that wrench, right? All the contribution of turning that wrench is this component of it, which is sine theta. So that's, if we know the length of all we need to know is the length of that moment arm, or the length of that vector r, and then the amount of force perpendicular to that, right? And that's going to be F sine theta. But just make sure you have your, you could put the force, you could put the tip here, you could put the tail here, and point in different directions. Just make sure you got that angle right. It's always that angle, that's the angle when they're tail to tail. So that's always your starting point for making sure you've identified theta correctly. Questions on torque? So this is the amount of twisting force, and then we know the direction of the torque vector is according to the right-hand rule. Righty-tighty, lefty-loosey. Questions? Okay. Next application. So when you have two vectors, there's actually, can you in your mind's eye see the parallelogram that's always formed by the two vectors? Can you see that? That there's, given any two vectors, there's a corresponding parallelogram. So what about the area of that parallelogram? The area of that parallelogram, everyone think to themselves, is that going to be a matter of dot product or cross product? Think for yourself, and I'll show you the area now. So that amount of area of that gold region, is that going to be calculated with something related to dot product or cross product? Yeah, go ahead. Either one, yeah. Okay, dot product because area is a scalar. Okay, does that agree? Disagree?
I disagree.
Okay.
I think it's a scalar because the area is maximized when the two vectors are at a 90-degree angle.
Okay, you think it's what? Wait, you think it's what? You said you think it's a scalar.
Cross product, sorry.
He's saying cross product. So basically when the vectors are parallel, what situation do we have when it comes to area? 0. And when do we get the best situation, or the optimal area? On the orthogonal. That's where it's going to be our biggest area. Therefore, cross product again. Cross product again. So let's see how this works. But this is a really good point, because he's saying the area is just a magnitude. Area has no direction. That's true. So what is it about the cross product that's going to give us the area? It's the magnitude, right? So now the direction of whatever that cross product vector isn't really, it's kind of negligible. We're just now talking about the magnitude of the cross product that's going to have some relation to the area, right? So let's call this vector A. And B, say. Okay, so how can I say what's the area of that? Area is, what is the area of a parallelogram? Is it magnitude of A times magnitude of B? What is it?
Base times height would be B sine theta.
So base times height, right? So what's the base? So base times height. What's the base? A? Magnitude of A. Magnitude of A. A is a vector, so base is magnitude of A. Okay, and then what is the height? No, don't just... How would I get, that's my height right there of this figure. So how would I calculate that? Yeah. No, you're making it way too hard. You're making it way too hard. What is the height? Yeah, it's just going to be the magnitude of B. But what? The part of B that's perpendicular to A, right? So it's the part of B orthogonal to A. So the height, so this is our base. And then the height is going to be, do you see that? Does everyone see that? The base is the magnitude of A, the height is going to be B sine theta. Look at that. What's that? That's exactly what the magnitude of the cross product is, right? So that's the magnitude of A cross B. It's the product of the magnitudes to the extent that they're orthogonal. So when are you going to get the maximum? When are you going to get the maximum area? When they're orthogonal, because then what happens when they're orthogonal? We know that the magnitude of the cross product is going to be the magnitude of A times the magnitude of B. That will be the cross product because it's maximized. It's the magnitude, the product of the magnitudes. And that's exactly what the area of the rectangle is. Base times height. Okay, so then I'll just mention this, and then you can. So, do you see, given those two vectors, do you see a unique triangle that's formed with all straight sides? With all straight sides. Can you imagine it? Write down what it is in your notes. Write down what it is in your notes. How would you, if you got vector A, was this one A down here? And vector B, what will give you the area of that triangle, that unique triangle formed by two vectors? When I put you to work later, you can compare your formula with the person next to you. But that's like falling out of bed, right? If you got parallelogram, that triangle should be easy. Okay, question on area. Okay, volume of a solid, like a cylindrical solid, this is a three-dimensional solid based on a parallelogram base, right? This is called a parallelepiped. Parallelepiped. Okay, and so really it's just a cylinder, right? It's a cylinder because all the way from the bottom to the top, this thing has the same horizontal cross-section, this parallelogram. See that? So this parallelogram, that's the base of it, is the same cross-section all the way from the bottom to the top. So just as a really general volume formula, the volume of this thing equals the area of the base. What? So if this is a cylinder, area of the base times what's the height? So area of the base times the height gives you the volume of this parallelepiped. Parallelepiped. So can you come up with a formula? Is it, first of all, is it dot or cross product? Or can you come up with a formula based on vectors A, B, and C? Based on using vectors A, B, and C that will calculate this. That will calculate the area of the base times the height. Let's put our heads together here. Break up into a group. Take about 3 to 4 minutes and see what you can come up with here. I want to come up with a formula of vectors A, B, and C that gives me the volume. If you have any, so don't get any help from any textbook or technology. We're trying to figure this out based on what we know about dot product and cross product.
A times B is a vector. A cross with B, A cross product B. Then multiply that vector by C. It's going to give you, that gave you the magnitude, that gives you the area of the parallelogram. Okay, yeah. That parallelogram. And then what's the thickness? Or how far back? If this was A and C, A crosses C would give you the area of the parallelogram. You also want the thickness in B direction. So it would be a second cross product. It's just like what we did.
Okay, so and what we want is an expression of vectors A, B, and C, but not an expression of the magnitudes of A, magnitude of B, and magnitude of C. So an expression that truly uses just the vectors A, B, and C.
I don't know, maybe it's I don't know if we need the parentheses. I think that's how you would do it. I don't know if we need the parentheses. What's the proper word for units?
Yeah,
I don't know if it's one of those things. So I don't know if you have to have the
Is that what you want? What do you want?
not orthogonal to those lines A and B would need to be pointed down a little bit. Because A and B are flat on the x and y. They're angled on the x and y plane though. So the x and y plane is flat.
Yeah, but you want to get it straight up.
Anybody think they got it? I bet you all got a good start. What about the area of the base? That's just a parallelogram. We just did it, right? So A cross B. So let's talk about that vector. Okay, so that's a vector whose magnitude is the area of the base, right? So if I were to draw that vector on this page, where would that, how could I sketch that vector on this page? A straight arrow, something like this. So this one here, is this A cross B? Maybe, or it might be a different magnitude than it's drawn, but does that give me the right direction of A cross B? Right-hand rule? Okay, so now what do I want to do? I want the magnitude of that times the magnitude of the height. So how can I show the height of this thing? Where's the height of this thing? Well, it's this right here, right? So, yeah.
Magnitude of vector c times the cosine of
Okay, but again, our goal is, so you're thinking now cosine?
Yeah.
Cosine, so we want to take the part of this that's in the direction of the height. What's that? Dot product. You see that? We need the part of C that's in the direction of the height. And when we do dot product, do we have any magnitudes now? Because we just get a scalar. Did anyone get that before I did it? Anyone have it? Right, so what? We need the part of C that's in the direction of A cross B. And then we just want the magnitude of all that. That's dot product. That's exactly what it is. It's the product of those magnitudes in as much as they're in the same direction, right? So the part of C that's in that direction would be this right there. Dot product with the area of the base then will give us the magnitude of the volume. So it's both. It's both. Both are involved. Do you follow it? Does it make sense? Anybody have a question? Yeah.
We did it another way.
Okay.
Now I'm not sure if it's the right one.
Okay.
So instead of doing phi, we did 90 minus phi for that
Okay.
theta or for that angle.
This angle here.
Yeah, that one.
Yeah.
No, the angle till vector b.
Yeah, but that's not 90 minus that because it's in a different direction.
Okay, that makes sense.
This is in the plane of A and C. So this is right here is in the plane of A and C. Yeah, this is in the plane of A and C. Oh, wait a second. Yeah, no, okay, sorry. So if it's this, we really don't know where this is relative to the planes of A and C and A and B. So so maybe. So if you anyway. So suppose that vector A cross B is in the plane of C and B. That's possible. That's possible. Okay. And so then you're saying that this is back here. This is 90 minus. Yeah, 90 minus phi. Okay.
Yeah, so we did a cross product, where that would be the magnitude of c
Mhm.
times cosine of 90 minus phi as the height, but I don't think that would.
No, that's not the height. That times cosine would be this. That would be right there. That would be magnitude of C times cosine of your 90 minus
No,
phi.
sine of.
Sine. Okay. Sine would be this. Yep.
Would that be height or would that
Yeah.
be?
Right, so cosine of an angle is equal to sine of 90 minus the angle. So yeah, that's true. You're right. But cross product of okay, yeah, I have to think about it, but it's make sure you understand this because this is a nice clean version of it right here. So yeah, so I'd have to think more about what you did there. Okay. Any questions on that? Well, there's three kinds of multiplication of vectors. So there's no time. There's no times. You always have to say what kind of multiplication you're talking about. A cross B is this vector here, and we want the height. So we want this much of it. We want this much of A cross B. So we're actually saying that's the part of C that's in the direction of A cross B. So what is that? That's magnitude of C cosine phi, right? So what is that? Principal. That's principal. What is it? Dot product. So yeah, so say dot. Don't say times. Say dot. Because there's three kinds of times with vectors. There's three kinds of multiplication with vectors. So A cross B, take that vector, dot C, or dot product with C. That gives you the volume. Because that gives you area of the base times the height. Area of the base. So you could write it this way, and you can see it. Right, area of the base times the height. Right, because that's dot product is product of the magnitudes to the degree they're in the same direction, which is cosine. Okay, so let's talk about lines. Lines in space. So we're going to kind of change gears a little bit here. But we'll need all this stuff. All this stuff about dot product and cross product as we get into lines and planes is going to be crucially important. Okay, so in 2D, what do we need for a what do you need for a line? Yuck. No. That's better. Okay, so I got the point here, 1, 2, 3. And so if you had a point in a plane, what else would you need then to write the equation of the line in a plane? Another point would work. This is an algebra question, 8th grade, freshman year. What do you need to write the equation of a line in a plane? If you had a point, slope, or rate of change, right? Rate of change. So we like rate of change better than slope. So yeah, so if you had a point and the slope or the rate of change, then that would determine a unique line. But what's the slope or the rate of change in 3 dimensions? What's the slope or the rate of change in 3 dimensions? We'll answer that question in a few weeks, actually. But do you see that that's kind of a ambiguous question? It's like, well, what do you mean, slope? Or because you've got now we're in space, right? So instead, we will specify what a point and a direction. A point and a direction specified by a vector will make a unique line. So here's how it works. First, we write the point as a position vector. So what's the position vector for the point P? right? That means put the tail on the origin. The position vector is where you put the tail on the origin and the tip at the point in question, and then the vector is simply the components are the same as the point, right? Okay, so that's my vector. And that's the vector corresponding to my point. And then from that point, we're going to specify a direction, right? So the line is in the direction of V from that point. So here is now the vector 1, -2, -1 with its tail at our point. So then the line is formed by what? All scalar multiples of our direction vector. You see that? If I take every possible scalar multiple of that direction vector, the tip of that resulting vector will then sweep out all points of the line. See that? So if I scale the direction vector with all real numbers, do you see that all the resulting points will form a line in space? Blank stares. All my life, blank stares. Yeah? Do you see it? So therefore, all we need to do is add those two vectors. We add the position vector for the point plus every possible scale of the direction vector, and the resulting vector will be all the points on the line. So do you see that the red vector is going to be all possible points on the line? Does it make sense? Let me give this a turn. Sometimes as soon as you start to move it, you can see a little better. There we go. All right, so how do we form a line? Position vector of a point plus all scaled versions of the direction vector added together make that red vector, and that red vector then is giving me the coordinates of every point on the line. You don't see red? It's dark red. The screen isn't great. It's a little more, it's brighter red on my screen.
The one that's stationary is black.
So this is our P. We'll write them down here. This is P. This is what we call V. Or actually, so it's going to be all scalar multiples. So T is going to be our scaling factor on V. And so then the resulting vector is so R, that's this. R is going to equal what? P?
Sum.
The sum, right? It's going to be the sum of P plus T times the direction. All scaled versions of the direction vector plus point P then will give us all points on the line from a zillion miles that way to a zillion miles that way. Now, so normally they call this point R naught because this is a point on the line. This is denoted R naught. Okay, and so it has components x naught, y naught, z naught. Our direction vector t times, and the direction vector is often a, b, c. And then what is r? R is all points on the line. X, y, z. So therefore, start x, y, z equals x naught, y naught, z naught plus t times ABC. So I want you to identify, just take a minute, talk to the person next to you. What does every symbol, there's a lot of symbols there. How many? 10 symbols, right? 10 symbols. What does every symbol mean, and which of those are varying, represent variables, and which of those represent fixed values? Which of those represent variables, and which of those are fixed values? Talk to the person next to you. So what does everything mean? And then which are variables, which are fixed? So, x, y, z here on the left. Variable or fixed? What does it mean? So how would you describe what this vector x, y, z is? It's crucial. Okay, so but what's the meaning of it? So yes, that's a variable vector, right? Those are all variables, those components. What's the meaning of that vector over there? What's that? If it's a variable, it's not a point on the line. Yeah. All the points of the line. This is all the points of the line. Okay? So in my equation of this line, what am I going to write? X, y, and z. If it's the equation, if I'm writing the equation of the line, I'm saying all points, such that what? What about x naught, y naught, z naught? Known or variable? Known. And so this would be 1, 2, and 3. So it's our known point on the line as a position vector. Okay, what about t? Variable or a known value? Variable. And what is the meaning of t in the situation? What's the meaning? How much we scale the direction vector by to get our point. How much we scale it by. Do we go 100 that way? Do we go 50 back this way? Do we go a half this way? Do we go -3? So by letting it be every scaling, then we get every scaling of that direction vector. Okay, what about ABC? Known or? For this? 1, -2, and 1. -1. So this is the general form of the vector equation of a line in R3. This is the equation of the line that we built based on P 1, 2, 3 and the direction 1, -2, -1. So what do you notice about this? So is that the only point on the line? How many points are on the line? So could I pick a different point to put here?
Yes.
As long as it's on the line, will it generate the same points?
Yes.
Yeah, this could be any point on the line. This could be any point on the line, and as long as it's a point on that same line, I'll get the same set of points, just generated a little differently, right? They'll be just generally generated differently. What about the direction vector? Is there any other way to write that?
It could be a different magnitude opposite.
Could I do -1, 2, 1?
Yeah.
Will I get the same points on the line? Get different points?
1, 2, 1? What'd you say?
-1, 2, +1.
You gotta
Is it the same line or not?
You get the same point.
So if you get the same points, is it the same line? Yes. The same points are the same line. If you get the same set of points, it's the same line. Okay? So, was there a question? Someone had the... No. Someone raised their hand. No, you're fine. You're fine. Okay. So, what's the deal here? I could have any point on our line to be my point. I could have any version of any vector that's parallel to this here. I'm going to get the same set of points, so I'm going to get the same line. Yeah, go ahead. Yeah, but do I have more choice? But what I'm getting at the moment, yes, it's a little bit. But what I'm getting at the moment is there more than one b for a particular line? No, b is the y-intercept. B is the y-intercept. No, right? If you have a particular line, it only has one y-intercept. And then what about slope or rate of change? Can I have more than one slope or rate of change for a particular line in R2? No. There's b is fixed. The rate of change is fixed, right? Change in y over change in x. This is a different beast. This could be any point on the line, and this could be any vector parallel to a given direction. And I'm going to get the same set of points. All right, so how are points then, how can we get a list of points that are on this line? How would we generate points on this line? What would we do? Yeah, we get different values of t, so let's do it. Ready? So make it easier on ourselves. Let's do t equals 0, 1, -1, and 2. That's fine. So what are we doing? We're gonna generate 4 points on this line. So when t is 0, I'm talking about the red, right? I'm going to write r, but as a point, okay? R is going to give us the position vector. And if it's the position vector, then it's pointing right at the point in question. So when t equals 0, what do we get? That's our point P, right? That's our point P. T equals 1. You got 2, 0, 2. Does somebody else get that? When t is -1? 0, 4, 4. Everyone see how we're getting those? You're able to do that? How does the equation generate points? By putting in a value of t, you scale the direction vector a certain amount, and you add your original to the scaled, and then you get a new point on the line. T is 2, you get 3. I heard 3, -2, 1. So these are all points on the line. So how are points on the line generated? Changing how much you scale the direction vector, or changing the value of t. Different values of t then generate, and that's like this is like the animation I was showing you, right? The end of the red vector are all points, right? Points on the line. And how is it changing? Just simply by changing the scale on the direction vector. Scaling the blue one. Every time I rescale the blue one, I get a new point on the line by the red one, by the red vector. So then any of these points or any other points on the line we could write right there, and we'll get the same line, just written in a different way. Any vector parallel to this one I could put here, and I'm going to get the same line that I'm showing you, right? So there's a infinite number of ways to write a line. And there's 2 different ways to have an infinite number of ways, right? You can change the point, any point on the line, and then you can change the direction to be any vector parallel to a given direction will still give you the same correction. Okay, so now look, we could actually do the math here on the right. Some room here. If I do the math, if I do the vector math there on the right side, what do I get? So I say x, y, z equals. If I want to write that all as one vector, what would it be? Yeah, that's just, right, scalar multiplication and addition, right? So what would the x component be? 1 plus t. What would the y component be? 2 minus 2t. Everyone see it? And 3 minus t. So what I can do here is I can now separate out the components. By separating out the components, what does x equal? 1 plus t. Y equals 2 minus 2t. Z equals 3 minus t. So this is a different way to express the exact same line. So this is down here, this is the vector equation of the line. This is called the parametric equations. And remember in Calc 2, you did parametric functions, right? Parametric functions. So vectors and parametric functions are like twins. It's just like two different ways of writing the same thing, right? Given a parameter t, every parameter t generates an ordered triple, x, y, and z. Well, that's exactly what we did up here, right? So there's the parametric equations form of the line, and there's the vector equation form of the line. All right, so let's just do a couple quick things for your sheet. So we'll call this the line that we worked on. We'll just call that capital L, okay? Or L1, okay, L1. So L1 was the line that we made as we talked about all this. So write the equation of the line parallel to L1 through the point 5, -2, 8. Call that number 1. Yes, this is for the sheets. This is for the sheets. No, you don't have time. At what point does L1 intersect the XZ plane? Okay, so that's it. That's the whole. So I want you to write the equation of the line parallel to L1, but through the point 5, -2, 8. Write that in vector form and as parametric equations. And then second question is, at what point does L1 intersect the XZ plane? We don't have time for this. Just do number one. Just do number one. If you followed what's going on, you should be able to just write it down. Yeah. L1's the one we just did. L1's the one we did down here. So I want a line parallel to that. Just write the equation parallel to that through the point 5, -2, 8.